Okay, here we are. So I think it's working properly. Okay, so the pumping lemma says that whenever you have certain number of states, at certain point, if you want to accept a string that is longer than the number of states you have, for example, you have 1, 2, 3, 4, 5 states here. And you want to accept a string that is 10 states, 10 symbols long. String consisting on 10 symbols. The pumping lemma says that if you want to accept any string that is longer than the number of states available, forcefully, you need to have a loop somewhere. So let's suppose that this loop goes something like this. And this is drawn in the book as dashed dots, just to represent you are looping here. So by doing this, then you can see that you can accept a string with 10 symbols. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. With this modification, you can do this. However, this is stating also that because you needed to add a loop, which is this part, then you are able to repeat this n times. You cannot limit how many times you allow this. So if you can repeat, in this case, for 10, it means that it can also repeat by larger numbers, like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So you would be accepting also by 416 and other numbers. Maybe if we list them in order, the shortest path would be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Sorry. 1,
Excuse me.
3. Yes?
Isn't there should be a state in the like intersection of this lines? So, the loop does mean that it returns to the same state.
Well, yes,
Yeah?
the principle is the same. In this case, yes, what Dima is saying is that we can, that I looped and these are disconnected. Saying that he wants to go back to exactly the same state and then do something like this. Well, the principle is exactly the same. Yes. Usually it's explained like this, that you have to loop to the same. Exactly the same will happen. We will have the same problem I want to illustrate. So it's equivalent. I will continue doing the previous one. The problem will be exactly the same because we are adding a loop here. So in order to get from here to here, well, at least the change here is that at least you must do this once, and the other one you can just skip it. But also I want to show, oh yes, I see, sorry, it's not the same because I cannot do this several times. Sorry, yes. So what I want to illustrate is that you can go back to exactly the same one and then continue to this. Yeah, it's not the same, sorry. I got distracted. Okay, so it is very important thing here. Let me erase my counts. The important thing here to see is, okay, let's begin again. Sorry for my my error. Okay, so we have we have 5 states originally. 1, 2, 3, 4, 5. So if we want to accept string that is longer than 5 states, we need to add a loop. If we add a loop, then we can count 1, 2, 3, 4, 5, 6, 7, 8. For example, we can accept strings of 8 symbols. Or we can do 4 more if we go through the loop 2 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Or we can do more times. 11, 1, 2, 3, 4, 5, 6, 7, 8, 14 states, etc. 14 symbols. etc. So if we aim to accept a string that is only eight symbols long, in this case it would be for the homework like x to 8 times. The problem is that I had to add a loop here. If we have a loop here, then it will allow me to accept other number of symbols like 11 or 14. And if we are allowing this, it means our number can be divided by a certain number of times that are here that are not allowed or shouldn't be allowed. So if we have something, for example, that accepts exactly 7, and I want to augment it because 7 is prime, a prime number. If we want to augment it so that it can accept strings longer than 7, then there are two options: to add more states or to add a loop. But if I add a loop, then I will add a lot of strings that are not prime, a prime number. So this is how this is demonstrated by using the pumping lemma. For the other case, using squares, the problem says, show that the language xn, so that n is m squared for some m in natural numbers, means that we are asking for any number of repetitions of n that are a squared number of some other number. So for example, we can think of m, if m is equal 2, then n would be 4, then we need to accept 4x. If m is 3, n would be 9, so we must accept exactly 9 x's, and etc. So we are looking for a language that accepts these strings, and because it's from n, we should start with 0, so it accepts the empty string. For 1, it would be 1 string, etc. So this is very bad drawing because it looks the same. Okay, this is better. So it's lambda, the empty string, or only 1x, 4 x's, 9 x's, etc. So we can think of doing this exactly for certain m less than 100. If we do this, it's a finite language. And we have seen that for any finite language, we are able to build a DFA. So it would be a regular language. However, if we want to do it for an infinite number of strings like this, because this continues, then it means we need to use loops. And if we use loops, then we allow the repetition within, and the pattern does not allow repetitions here. So for example, if we allow to repeat this part, if we accept 4 and loop this one, then we would have 8, for example, and 8 is not an squared number of any other m, as you can see. Or if we are accepting 9 and we loop the whole thing, then we would be accepting 18. So the task here is to demonstrate that these squared numbers cannot be repeated within other numbers. That any squared number does not form part of any other squared number in terms of repetitions. That's it. If, for example, we have 9 and we repeat 9, which is a squared number of anything, if we repeat it, it will be 18th or maybe 27 or 36, etc. And this is not a squared number, and this is not a squared number. Maybe this is an squared number, but the other ones are not. So the problem is that I would be accepting numbers that are not within the language. So by contradiction, the only way of doing this is that we would need an automaton with non-finite states. And of course, this contradicts the definition, so it cannot be built. I don't know if by this means this is clearer or worse.
Yes, I think that it's more clear, but I need to recap.
Yeah, so you can try to think this on this way. The main problem is the repetition, that if you want to accept a string that has more, which is needed, so you need forcefully, you need to have a string, a DFA that has a loop, because you are trying to accept an infinite language with a finite number of states. So you need loops. And if you add loops in any part for these kind of languages, n is prime or m squared, or any number that is a square of another number, then you can't rely on loops because of the way of calculating this. This is how the pumping lemma is applied to solving these problems. So perhaps in my first explanation, I didn't refer the pumping lemma, but it's exactly the same problem. And the other way is to say that you cannot calculate this precisely because you don't have any ability of calculations within these machines for obtaining which numbers can be divided by others. Yeah, so I hope this is a bit clearer.
Yes, thanks.
Thank you. So if you open the Moodle system, perhaps you were able to see a resource. Let me see if I added it. Just before the homework, I added both the Thomson method and how to obtain the regular expression from an AFD. Let me show you this. So you can see a lot of things that are in gray. Please don't take them into account. It's just my view. But what I want to show you is this one, which is how to obtain an AFN with epsilon transitions from a regular expression, and how to obtain the regular expressions from an AFD. So previously, last class, we saw this algorithm, which is called the algorithm of Thomson and Ritchie. And of course, I wanted to mention them with a special mention because they are the Unix creators. And perhaps that sounds like a very, very old thing, but nowadays we are still using the sons of this system they created. If you use, for example, Android or iOS, or even Mac OS X, those are direct descendants of these early systems. So they are still used. If you use Linux, that's not a direct descendant, sorry, but it's inspired by all of those things that they created. Maybe in another class we can talk about this. However, they created a particular way of solving things, which nowadays is still used, as we said before. However, those were restricted by patents, and patents mean money. So when Linus Torvalds decided to create Linux, he tried to avoid all those patents, and that's why Linux is not a direct descendant of the original Unix, which is not bad. It doesn't mean it's a bastard son. I don't want to say this, but it was just to avoid paying royalties. so that way Linux can be free and completely free. And Mac OS X, for example, it cannot be free, or iOS cannot be free. Even Android cannot be free. But well, this is just a technical issue, like not so important for us. But what is important is that we are using the algorithms developed by these two people, and precisely they needed how to obtain, they needed a method for obtaining a deterministic finite automaton so that they could speed up their compilers. They were working on early systems where every little bit of memory was really, really important. So in these systems, you wanted to use or to take advantage of this small memory and speed. So in order to compile a whole operating system, you needed to make it really, really optimized. So this method allowed to obtain DFAs out of a regular expression that could be processed in a very quick way. That's also why we don't want it to be non-deterministic, because if it is not non-deterministic, you need, as we saw before, we need to explore and go back and then explore again and then go back several times. When we convert our NFA to a DFA, then we know exactly what to do. And that's part of the optimization. So it can be regarded as well as an optimization method for use in those times where they were creating a new operating system and everything needed to be optimized. Nowadays, the fashion of creating new operating systems and doing compilers by hand is not so fashionable, it's not so in. However, as basis or as a part of computer science, it's still very important to know how all this is done. Well, so if you want me one of these days to talk about old computers and how this appeared, tell me, and I will be very happy to talk about this. However, we need today to see the method that the contrary method. So this method here is how do we obtain a regular expression out of a DFA. I think that if you click the link here, the resource will be in English. It's from, yes, it's in English. So for English-speaking people, don't worry. Even if the name of the link is in Spanish, when you click it, you will see the resource in English. This is taken from the Zipser book. And here is the definition of a regular expression, which is the same one that we have seen in this course. Is any symbol for any symbol in the alphabet, or an empty symbol, or an empty string, or empty language. Sorry, this would be lambda for Zipser. This is empty symbol, this is empty string. Or the union of any two regular expressions, the concatenation of any two regular expressions, or the clean star of a regular expression. And that's it. It's the same that we are seeing with Brookshire. So sometimes I want to introduce you to different notations so that you don't feel strange when you are reading a different book. So I will explain this method for you. Well, this is exactly the thing that we have been doing before. This is the clean star, etc. But let me show you better with the whiteboard. In case you have any doubt, however, you can come to this part of this book and maybe you can solve some questions. Okay, so after this long introduction, we will be working with the same example they are walking through in case you want to check it afterwards. Okay, so the example is this one. So we will be working with this DFA. Just let me verify it is exactly the same example. Yes, that's it. This is shown in page 76, in case you want to check it. Okay. So let me put a title on this. We have seen how to obtain, given a regular expression, how to obtain an NFA with epsilon transitions, and then convert this to a DFA. And today, we will see how to obtain a regular expression out of a DFA. So our example here is this one, and we will be, the first step for this consists on adding a new initial state and a new final state. In a similar fashion as we did before, for all accept states, we will concentrate in just a single one so that we can work also with only one initial state and one final state. Yes, so step one, add a new initial state and a new final state so that all previous accept state go to this new accept state and are connected with an epsilon. So this is step one. I will repeat this so that you know this is step one. Okay, once you have this, let me see if I can erase the green thing. Yes, I could. Good. Okay, once you have this, then we need to remove each state one by one. For this, we need to number states. The initial state will be always called initial or start, and this one will be always called accept. And we can number this as 1, 2, 3. And as always, we can use any number we want. However, we suggest that the previous initial state is 1, and the other ones can be in any order. Order does not matter again. Once we have this, then we will start with state number 1, and we will erase it. So this new erased state will be called qrip. That's why sometimes this method is called the qrip method. Why? Because we will be eliminating or ripping out states. This is where the rip comes from, ripping out, or also from rest in peace, so that we are killing them. But I think it's better to think on ripping the states. So we will be erasing this state. Now that we have this, we will build a new automaton that does not have this state. For this, we will iterate through all states. We will iterate by using two variables called qi and qj. So we will have our initial and our destination, our start and destination. We will just limit this iteration by saying that qe cannot be the accept state, and qj cannot be the start state. meaning that we cannot do simultaneously starting here and ending here, or we cannot start here and end in any of these, or we cannot start in any of these and end here. We will see this is iteration how it works in the next diagram. So we will start drawing the new diagram, and okay, we have the original start. And we need to see this one. We need to verify all possible connections with 2, with 3, or with accept. And we need to know what goes here on top of this. So we will make QI start. So this will be our QI. And when we work for number 2, this number 2 will be our QJ. Now we will apply 4 rules in order to build what will go here on this arc. Our 4 rules are R1, what went from QI to qrip. Qrip, remember, is the state that we eliminated. We will put this in action and it will be easier to see. It will be clearer once we are working on it. R2 would be a loop from what came from qrip to qrip. So if there was any arc going out from qrip and going into qrip, that will be R2. R3 would be whatever came out from qrip to qj. And finally, R4 will be if there was any direct connection from qi to qj. And finally, we will have here a regular expression concatenating R1, R2, R2 with a clean star, and R3 or R4. We add parentheses because this can get more and more complicated each time. You will see why and how. The logic of doing this is the following. Imagine we want to reconstruct how will, let me a different color. Suppose we want to know how to connect start with 2, which is exactly the same we want to do in our new diagram. We want to connect the original start with 2, yes? So in the original diagram, this green line is exactly this one to this one. Yes, so we try to reconstruct this, the original into the new one. So you can think of having here an invisible qrip, which is not existing anymore. It was here. So we need to consider everything that came into this state, which is R1, this one, everything that came out from the qrip, which is R3, or in case this had a loop, we need to consider it as well, and this is R2. And finally, if there was any previous direct connection, like the green one from start to 2, we need to consider it as well. So this is what this new regular expression means. It tries to convey what it was entering to qrip, what was happening to loop in qrip, and what was going out from qrip, or any direct connection we had from qi to qj originally. In this case, we don't have that one. Okay, so this is the general principle. We will apply this several times. Don't worry if you don't get it now. We will do it so many times that eventually you will get it. Okay, so let me erase this note. Okay. Okay, so for this particular example, where this is QI and this is QJ, for this example, we have that QI from qrip, it's an epsilon. Sorry, I forgot to add this. This is an epsilon. From qrip to qrip, there is no loop, so this is nothing. And nothing we will represent here like a line. Please be aware that nothing is not the same as epsilon in this case. So I know that epsilon represents an empty symbol, but in this case we represent there was no arc before. There is no arc present here. It's not the same as an arc with an epsilon because there is an arc present, but with an epsilon. No arc means nothing. So we put it like a dash.
It's opposite to epsilon actually, yeah?
Um,
Because epsilon is a way to transition from one state to another without any symbol, and this is like no transition
no
at
transition
all.
possible at all. Yeah, so that is not the same. Good. And R3 is anything that goes from our original. Oh my! I think my pencil died. I need to recharge it. So R3 is whatever came out from qrip to qj. So it's this A. So it would be A. I cannot draw with my finger. Maybe I can add. So this is an A. And finally, there is no arc previously from coming from start to state number 2, as you can see. I draw this green line just for explanation purposes, but the original diagram had no green line, so there is no connection. There is no direct connection from start to 2. Then again, we add here a dash. So finally, we have this combination, which is R1 followed by R2 and followed by R3 or R4. So in this case, we will have, we just copy them. We have epsilon concatenated with A. And in the middle, there is nothing. And that's not a problem. For this concatenation, well, I need, let me see if I can draw now. Yes. So we have epsilon concatenated with nothing, clean, and then concatenated with A, or nothing. And this can be written as epsilon concatenated with A, which finally is A. So that we'll put, what will we put here? Just an A. Now, in this step, you need to be aware that we need the presence of both R1 and R3. If for some reason R1 is present, but R3 is not present, it means this these two are not connected. Then if any of R1 or R3 are not connected, this part, the wall will die. This part dies. And if this and this die, then there is no arc. We will see some cases for this in the following elaboration. Okay, maybe there are a lot of questions here, but we will try to refine it by doing it many, many times. Okay, so we have finished for this QI and this QJ. Now we move our QJ to the next one. Now, this will be QI, and this will be QJ. So we will evaluate the same things for these two. And then we have from start to Q3 through qrip. Then we evaluate QI to qrip, epsilon. Qrip loop, nothing. Qrip to QJ, this is qrip to QJ. Yes, we have a B. By the way, this should be a B as well, sorry. We have a B. And then a direct connection between start and 3, there is nothing. If we write again our expression, it would be epsilon concatenated with nothing, clean star, and R3 or R4. It looks like this, which can be rewritten as epsilon concatenated with B, which is in turn B. So the label for this arc between QI and 3, or start and 3, will be B. And then we have finished for this one. Now we will do for QI and accept. So we are working for QI, and now QJ will be this one. Then we have again QI and qrip. This to this is epsilon. Then qrip to qrip, nothing. From qrip to QJ, it will be qrip to QJ. There is no arc, as you can see. There is no arc from qrip to QJ. Then we say nothing. And finally, is there an arc from the original start to QJ? No. So that's nothing as well. So you can see here that we need both this and this. And we said that if there was nothing on any of these, or R1 or R3, then this part does not exist. And if also R4 does not exist as well, it means there is no arc from QI to accept. And that's it. Yes? Okay, so we have finished for all the possible states for QI, so it's time to move our QI. We have finished for this one, which is QI. Now I move, this cannot be QI because it's dead. It doesn't exist anymore. So the next QI will be this number 2. So this will be the new QI. And this will be, this is always the accept, no, the start. Okay, so we will choose this as QI, and this cannot be QJ because we have this rule, QJ cannot be start. So QJ can be this one. So we will work for this QI and this QJ. And we start doing the same questions. R1, R2, R3, in order to connect them. The question is, what is the label for this arc? So for QI to qrip, now we have to ask from this to this, from QI to qrip, there was an A. Loop from qrip to qrip, known, there's no arc. And for qrip to from qrip to qj, yes, there is a B. And finally, a direct connection that existed before from 2 to 3, no, there is no arc. So it looks like this. If we write this, it will look as A concatenated with nothing, concatenated with B, or nothing, which is no more than AB. And that's it. So the level for this arc is AB. Yes, I think you are seeing better what are we doing. This represents how can I get from 2 to 3 through qrip if I erase qrip? Oh, well, you needed to go A and then B. You see? A, B, A, and then B. So exactly now, when we delete qrip, it will be the same, A, B. That's what we are reflecting here. That we are trying to reconstruct the original machine without using this state. Okay, we have finished for this qj. We put it in green. So we need to move this qj, and the only option is this one. Now my qj will be this accept, which means we move qj to this one, and we are trying to obtain the level for this arc. Note that all these arcs are directed. It's not the same from qi to qj than qj from qj to qi. There's always a direction, okay? So we are doing qi to qj. And we will do the same to ask the same relationships. Q for R1 from QA to QRIP, again the A. Again, there is no loop here. And for R3 is how can I get from QRIP to accept? And there is no link again. So we put this, and a direct connection between QI and QJ. Did it exist before? Yes. From 2 to accept, we have here an epsilon. So we add an epsilon. And note what will be happening here. We have R1 and nothing, and again nothing, or epsilon. So remember we said that if we didn't have R1 and R3 simultaneously, the left part would die. However, the right part does exist, so we will keep this epsilon. So the label for this arc is epsilon, just as before. We can think of this as from 2 to accept, qrip never had anything to do. We don't need qrip to reach accept. There is only a direct connection. So we don't have to go through all this, only epsilon. Okay, so it seems we have finished for this qi. Why? Because I cannot choose another qj. This is not possible. This is already done, and this is already done. So we have finished for this qi. Let me erase all colors. I will redraw them. So this is 2, this is accept, and this is 3. Okay, so I need to move my qi again. Now this is my qi. Qj, this cannot be qj, but this can be qj. So this will be qi, oh my God, qi, and this will be qj. So we will be trying for this qi, and sorry, this should be blue. qi and qj. Again, in terms of arcs, what I'm trying to see is the level from this to this. I'm trying to obtain the level from 3 to number 2. So let's do the R1 to R4 again. We have QI to QRIP, meaning 3 to QRIP. Yes, we have a B. There's no loop on QRIP, and it won't be until we change qrip. And from qrip to qj, it's from qrip to qj, this is qj, it will be an A. And finally, direct connection between qi, that is 3, to qj, there is an A, is this arc. So we write this. We have B, nothing, A, or A, which is simplified to BA or A. We have this regular expression that we will write on this arc, BA or A. So for going from 3 to number 2, I can use BA by doing this, BA or A. This is what we are expressing, BA or A. And now in a single arc, it says BA or A. Please note that adding a regular expression on an arc is only for this method, because this is not a DFA or anything, because from the point we are using this, it wouldn't be correct. It's just for converting into a regular expression. It's just for this method.
Can I ask a question about?
Yes.
You said that if there is neither R1 or if simultaneously R1 and R3 are empty, no connection, then we will have no connection from one state to another. But
yes,
as far as I understand, this combination of rules, R1, R2, R3, or R4, they represent a way to get from one state to another without directly writing this ripped state.
Yes.
But if we did not have, for example, R1, but there is R2,
yes,
there is no way of getting through the ripped state.
Yes, right.
But how then? But if there is no way, then why would we write that expression?
Yes, I think
I'm not sure.
I think we are writing more than needed, so to be very methodic. So if I understand your question is, why do we write this part?
No. For example, imagine that we did not have this connection from state 3 to ripped state, which is represented
Something
by yes. Then the R1 would be empty, right?
Yes.
But we will still have the regular expression in the end.
Yes, because as I told you, this part dies, but not this one.
So the
A.
So the left part dies if any of R1 or R3 is empty.
Yes.
Any of them.
Yes.
Not both.
No, any of them.
Yeah. That's why I was asking, because I thought that there was both of them needed to be empty, and I did not understand why. Thank you very much.
Thank you, Dima. I think perhaps I didn't express correctly. So we need both to be present in order to have this left part. If any of them is not present, then the left part completely dies. The left part. And the right part dies if there is nothing over there, and the whole arc dies if there is nothing from the left part and nothing at the right part. Okay, so let's continue. We have finished from this qi to this qj, and now there is another option for moving this qj. We can draw this in green. and is to use this as qj. So now we have, we want to see if this arc has a label. We erase this again, and we will try to see R1 is qi, which now my qi is this one, to qrip is b. The second one is nothing because there is no loop. The third one is qrip to qj, and there is no connection from qrip to qj, so it will be nothing. So this makes the left part to die, and the right part would be a direct connection from qi to qj, which there is an epsilon. So when we write b and then nothing or epsilon, this part dies because R3 is not present, but we keep this part. So at the end we have epsilon. So the arc from qi to qj, which is from state 3 to accept, is epsilon. And we have finished for this qj. And we have finished also for this qi. And there are no more states for qi because qi cannot be accept. This cannot be qi because of this rule. Qi cannot be accept. So we have finished for this part. So we have successfully eliminated qrip from this automaton, and we need to keep further eliminating all states until only this start and only accept are left. And we will use the resulting arc as the resulting regular expression. So let me copy this into the next page. So now you see what we are doing is has sense, right? Is making sense.
I have a question.
Please.
What happens with the loop of B in the state 2?
Yes, in which state, sorry?
In the state 2,
Yes.
the loop of B.
Oh, yes, sorry. I'm completely wrong. Sorry. I'm missing something very important, which is what happens when qi equals qj. And of course, that can happen as well. Yeah, and I was completely forgetting that. Okay, so we have not yet finished. I know if Cesar, that's your question as well, because you have raised your hand.
No, my question is about if there is a canonical way to select the state that we are going to rip, well, select our qrip.
No, and precisely depending on which state you rip before, you will have a different resulting regular expression, but equivalent. All of them are equivalent anyway. So
Okay.
canonical way, it depends how you label them. Usually 1 is the initial state, but if this is 3 and this is number 2, and then you rip first number 2 and then number 3, it depends on you. So there is no a canonical way, as you put it.
Okay, thanks.
Okay, thank you, and sorry for forgetting this. This is very important. So what happens if I want to do this qi and qj? Well, I cannot, because as we said before, qj cannot be start. So this is not possible. And what about this, making this qi and this qj? Well, it means we are exploring this arc, and this is possible. So we will see what happens when we do this. We have qi to qrip, meaning from qi to qrip. It says A. And then qrip to qrip, nothing. Don't get confused with this loop. It's different. We want qrip from qrip, and there is no loop, so it's nothing. Then qrip to qj, and we have qrip to qj. That I think is the question that we had before. What happens with this one? Qrip to qj is a, and also the original from qi to qj, which is this one, this loop that we were forgetting. So yes, we have b. So at the end we have a, nothing, a again, or b, which can be simplified as AA or B. And this is the label for this one, AA or B. Good. And now we have finished for this one. And we also need to examine what happens for this QI and QJ. We will see. So we do again the same. We will use different color. We are examining this arc. So we have from QI to qrip, B, qrip to qrip, nothing, qrip to qj, qrip to qj is B again, and finally there is no direct connection from qi to qj. So we have B, nothing, B, or nothing, which is simplified to BB. Now we have really finished. Sorry for that omission. Now we can continue to rip another state. Thank you for your question. Okay, so also another very good question is what happens if now I rip this or this? How do I know which one is better? Well, there's no suggestion. You can rip this as well as this one, and yes, the resulting regular expression will be slightly different, but it will be equivalent. So now this will be our new qrip state. And we begin again by using qi, and this cannot be qj, but this can be qj. This is a start, and this will be qj. So let me copy the rules from before, that we will keep using them. Okay, we have, and now we want to copy this without the qrip, and we have the start, and we are examining for this connection. This is ugly. Number 3. Let's see what is the label for this arc. We have qi from qrip to qrip, qi to qrip, A, and qrip to qrip. Now we have this loop, and will be present in all of our arcs. And qrip to qj is this one, AB. And also a direct connection between start and 3 is B. So now our expression gets a little bit more complicated, because it would be A or AA or B clean, or AB, or B. Maybe not so much, we cannot simplify it so much. Maybe we can do just AA or B clean AB, or B. Maybe there's no need for those parentheses, but well, let's keep them. So you can see it's getting more and more complicated, right? Okay, we have finished with this QJ. And can this be QJ? The blue one? Yes, right? The only problem is that QJ cannot be start or QI cannot be accept. So now we will evaluate for this one, which means we are trying to see the label for this arc. But I think it'd be longer, so I need to draw a longer line. That's it. So what's the label for this one? I'll erase this and calculate again. We have QI to qrip, A. Actually, these are the same. I shouldn't need to erase each time, but well, it's just to remember how to calculate them. qrip to qrip, A or B. And now we have qrip to qj, which is this epsilon. And qi to qj, an original connection between start and accept, nothing. So we have A or A or B, clean, or epsilon or nothing. This part will die. And we finished with, if we simplify, A or B, clean. That's it. And we have finished with this one. And also we have finished for this as QI. So now we will change our QI. QI can be only moved here because this cannot be QI. So this is QI. And let's see also QI to QI. So this will be QI to QJ. So the same will be QI and QJ. Now we have QI to qrip is BA or A because of this one. Qrip to qrip is AA or B, and then qrip to qj, AB, this one. And a direct connection from QI to QJ, there is already, so it's BB. So the whole expression says BA or A followed by AA or B followed by AB or BB. And all this beautiful thing goes here. Let's make it a bit smaller. That's it. Okay, now let's move QJ. Now QJ will be this one. We are working on this QI and this QJ, meaning the connection of this one. So let's see, QI to qrip. QI to qrip is BA or A. Maybe I didn't, it was not needed to erase it. Okay, BA or A. Qrip to qrip is the same as always. And qrip to QJ is epsilon. And and QI to QJ, this is also epsilon. So we have BA or A followed by AA or B concatenated with epsilon or epsilon, which can be rewritten as BA or A concatenated with AA or B. Concatenation with epsilon can be omitted, but this cannot be omitted. So please pay attention here, because I cannot eliminate an union with epsilon. I can omit this concatenation with epsilon, but union with epsilon never can be omitted because it's different. It's not the same. Let me write it here. Any symbol A concatenated with epsilon is A. But if you do this, any symbol union epsilon, you have to leave it as it is, because it's not the same, because you are saying you can use this, but also you can ignore it. And if you decide to eliminate this part, then you are eliminating the fact that it can be ignored. So in this case, it adds information. In this case, it does not add any information, because it says you can read an A and you can read many empty spaces. Well, those not are spaces, but empty symbols. Well, it doesn't matter. Yes, so please remember, concatenation with empty symbol can be eliminated, but union with an empty symbol cannot. So in this case, we keep it, and this will be our, let me make it smaller before. This is our label. So we have finished, no, not yet finished. Yes, we have already done QI and QJ, QI and QJ, QI and QJ, QI and QJ, and this cannot be QI. So we have finished. We are closer to the end. Don't despair. So again, I will copy this to next page, or maybe no, maybe we can do it here. So I'll erase this and this. And now there is only one state I can rip. This will be qrip now. And there is only one way to select this qi, and this will be qj. There's no other way to choose them. So what we have now is that we will have start connecting directly to accept. So we need to know what's the label of this beautiful thing. So we will see. We have R1. Actually, we already have them. R1 would be this one, QI to qrip. So this is R1. R2 is qrip to qrip. So this is R2. R3 is from qrip to qj. So this is R3. And finally, R4 is what we had originally. So we need to concatenate them and write them accordingly. So it's this one, and this will be concatenated with this one, with R2. Clean star, concatenated with R3, or R4. So that's our beautiful regular expression obtained from this method. And yes, I know it's a bit ugly, but well, I'm sorry for that, but it's a long regular expression. And of course, there is no guarantee that is the best or the shortest regular expression. Yes, but however, it's equivalent to exactly the first language we had. And well, this is how it is obtained.
And now we build an FA out of it and convert it to DFA.
No, well, you can. Actually, you can. It's easier to automate this part than to automate the contrary, because in order to parse a regular expression to build a DFA, you need to use parsing techniques. And we don't have the tools yet to parse a syntactic, to parse a string syntactically. However, this, yes, we can implement it. So now I want you to try this on number 16. Well, not now, but it will be the only homework for today. Will be to do 16a. So this will be tarea, because that's in Spanish. I don't know why, but it says tarea 1.4, exercise 16b. But in this case, we want to obtain, now that you know the DFA, to obtain the regular expression. And that's it. Dima says that now obtain the NFA and and all that, but I think it's too much work for you, so no need. Only obtain the DFA to regular expression, and that's it, using this method, of course. So is exercise 16b, page 70. You know how to solve this using a DFA already. Is all strings, let me copy and paste in case you forgot. So this is 16b. It says all string consisting of an odd number of x's and even number of y's. I think for you it's not difficult to do the DFA, because you already know, and then obtain the regular expression by using the method we have seen today. Remember that we say that even or zero, because otherwise you will have a lot of more states, because you need to handle when it's not zero. So please add that, an even number or zero. So you will have a 4-state DFA, which is much more manageable. And then you start adding the initial state and the accept state. And then you will need to remove, to make the state number 1 qrip, and then you know how to do the state number 2 qrip, state number 3 qrip, state number 4 qrip, and then you will have your long and beautiful regular expression. Yes, and I hope that will be the last time you have to do this by hand. The idea is to automate all these things so that you don't have to do, in Spanish we say talacha, no? I don't know if in Colombia you get it, Christian, talacha. No, sorry. Talacha, I think, is a very Mexican word. Talacha means doing something routinely, which is very hard and repetitive. You have to repeat and repeat, so it's talacha. And also is when you change your tires and you take them to fix them and to add a patch to patch a tire, and that's called the talacha also. And it's a routine work, and it's consistent with the definition. So when we have something that it's very repetitive, like this sort of methods, well, we say it's mucha talacha, a lot of talacha, or talachudo, no? Very talachos. Okay, so, well, yes, I hope this is the last time. Do you have any other question on this?
I have a question, but I'm not sure if that's completely on topic. You said about the even numbers, even or zero.
Yes.
Can I ask, why do you not consider zero an even number? Like the definition of even number, I believe, is that it's represented as 2 multiplied by some integer.
Yes.
But 0 is integer, right? So you can represent 0 as 2 multiplied by 0. So it's even.
It should be even under those conditions. Yes. However, I have found some issues with zero sometimes, and starting, for example, when I say n, the natural numbers, usually I expect 0 to be included. Yeah, if I say that, I expect 0 to be included. However, some people say that no, that 0 is not included. So that's why we started this course by saying, well, okay, there is with 0 included, and if you don't want 0 included, then we have only the positive numbers, and 0 is excluded. Because notation changes sometimes. I agree with you, Dima. For me, I would say that's the case. However, I have had experiences from people with different backgrounds that sometimes say no, because 0 is cannot be, because, and they can argue because yes, there are reasons for which 0 is not even or odd. They can say because maybe it has to do because it's not positive, and for some definitions, 0 is even and odd numbers are only defined on the positive numbers. So with that kind of definitions, then you can argue that 0 is not even. That's why I stress, in order to avoid such confusion that 0 or even. Or maybe we can say that 0 is even from the beginning, right? But it depends. That's why.
I see. Thank you. Thank you.
Yeah. No. Thank you. Thank you. And well, I'm always happy to receive such questions, and all sort of questions. I'm happy to receive. Well, if there are no more questions, no, I will not finish here. Sorry, I will keep torturing you. Okay, Arturo, tell me.
It's a quite bad question, but I want to know.
Questions. Bad questions are those that are not made.
But it's because I know that is from the homework.
Yes.
That I would like to know which was the correct regular expression for the 16b.
Oh,
in order to do.
Obtain it. That's the.
You sure you want to know it?
Yes. Actually, precisely the answer to that you will obtain when you do the homework for today.
But it was obtained by the DFA.
From the DFA.
In the previous homework, right?
Yes, I think that your concern is that if I'm asked a regular expression so that I can get the DFA, how the hell can I begin from the DFA to obtain the regular expression, right? That's your concern. And yes, your concern is right, and I share it with you. However, I think there's no other way to obtain the regular expression. Just by trying to obtain it by intuitive methods, I think it's very, very difficult. So yeah, I cannot find another way of obtaining it properly. Because for sure you were trying to get it, and then you found some mistake, and then try to make it again, then another mistake, and again and again and again. And maybe I should give you an advice before, no? Like, don't try for more than 4 hours, because otherwise you won't find it. But yeah, sorry, next time I will tell you that this is a difficult question, and just try it. I mean,
Okay.
I really wanted you to try it, because that concern is precisely the one you have now, that, well, then how can I get this? Well, I think only from the DFA, only beginning with the DFA, which actually, if the question is write regular expressions, then it's okay. You are providing a regular expression out from it, and it doesn't say, and never use a DFA, because that's bad. So don't worry. But now, I think now you have the motivation to use this method, because there are some regular expressions that are very difficult to obtain with intuitive methods. So you need to use a method like this, and at the end it's also a little bit ugly, because, well, by ugly I mean talachudo, no? Which is a lot of talacha.
Yes.
Okay. So, and of course, always all your questions are welcome. Okay, some politics message. You have seen many times that you have been invited to vote for the academic vice rector or vice director. So please do it. Maybe you can say, I don't care about politics, but at the end you have some influence from decisions taken from that position that may affect you. Well, I expect positive impact in general. So please do vote. You should have received a place where to vote, is like the one to obtain a token, and from there the procedure is pretty easy. I saw that there was a very interesting translation, because it involved something related to hot springs, because it was a mistranslation from terna, which means group of 3 people, and it was written with M, so it says terma. Terma has to do with thermal waters, so that's why it says thermal water. So, well, for me that mistake was a bit fun. But, well, I think it needs to be clarified, particularly for English-speaking people, because maybe they will say, well, we don't know what to do then. So there is a link. Let me provide it for you, where you need to cast your vote. For casting your vote, you need only to provide your ID number, número de boleta, and everything is carried out here on that URL. So, well, I cannot tell you who is the good one, who is the bad one, because at the end the criterion is yours. Maybe I would just give some advice that maybe people from that are already working in our institute knows better how everything is moving, how everything works. So maybe that's the only hint I could give, but of course the last decision is completely yours. I don't want to induce any vote, just maybe if you have some more questions. And also, I had some personal experience with Edith, and it was a little bit unfortunate, because we were trying to have a co-direction of with a student, and unfortunately, well, she was so busy that couldn't come to meetings. So, well, maybe I'm a little bit biased with. I don't know. I had the feeling that she didn't care for the academic part, so playing an academic role, I find a little bit contradictory. But again, it could be just my own experience, right? So try to read the program, the plans for from each one of them and take your decision as you think better. Okay, so still 20 more minutes. Do you want to ask something or you want me to present you something? And you know what something is. Well, it's related to old computers. So if you want, I will give you a very short talk. And also another, well, sorry for talking about politics, but only procedure. The procedure is to select 3 people out of 3 with your votes. So maybe you can think, how come this is ridiculous? How there's a way to leave one out from 3? Yes, so maybe you have also this question. The process is for selecting a terna, a group of 3 people, and at the end, the general director of the IPN will select 1 out of these 3 people. But now the voting is important because he will say, well, I have 3 people. Then how much are they loved in the community? So then he will see your votes. So it's not only for choosing 3 out of 3, so also to see a ranking between these 3 people. So that's why your vote is important. And it's the vote of all community, of students, administrative people, and also professors. So that's why it is important. Okay. Now the talk. Of course, if you want to say anything, please interrupt me.
So for which we have to vote?
I cannot tell you, Arturo, because at the end it's your choice.
My decision. Okay.
Maybe I can just suggest not to select Dr. Edith because
For what use?
I think she's not so involved with the center because she does not care too much. From my viewpoint, she does not care too much. So if you want to choose one of the other 2, just go ahead. But of course, if anyway you think she's a good candidate, I cannot tell you don't do it. Just it's a suggestion, and at the end is your choice.
Okay.
A question: does anybody of the others have been in a similar role that has good performance?
Yeah, that's good question. Professor Eusebio has administrative experience. However, his experience is not in the center. However, as far as I know, he had good performance as administrative. So that might be a good candidate as well. The other candidate, Doctora Blanca, has been administrative, personal administrativo. She has been in the administrative role, but not as a leader. So maybe she has some experience. She knows very well how processes are taken out, how, for example, she has been helping in the process of reporting to CONACYT for being the PNPC, which is one of the things that make us have a good number of scholarships. And well, I think she knows this process very well, but she has not been as a head of coordinating these tasks. So it's like, I don't know, maybe even myself, I don't know exactly what to expect better from one or another. Maybe I would think maybe that any both of them can do a good job, I think, but it depends also what else you see, or maybe you can ask something and help us decide. I don't know.
Thanks.
Okay, maybe we have too little time now to present this, so maybe I will try to give you a teaser so that you come next class happier that you will not see a lot of horrible things, only methods and methods, mechanical methods, which are not so bad, you know, because they are very useful, but maybe they are a bit tiresome. So I will just present a little bit and then we will continue next class. So yeah, this is a little bit like a movie. Can you see my screen? Okay, so do you know where this movie scenes are taken from?
Metropolis.
Good, yes. Well, it's a very, very old movie, so I think each time is farther and farther from us, but it's one of the first science fiction movies which is complete. It's made by Fritz Lang in Germany, and it depicts a future with a lot of, you can see flying things. Of course, they look like airplanes from Second World or First World War, and a lot of cars here and very, very big buildings. So these scenes are, well, I decided to put them because I think it resembles a little bit to this place. Of course, my pictures are so bad, but it looks a little bit like this futuristic town. It's Seattle, but seen from the outside. So perhaps, or maybe I'm having too much imagination, but at least at the back part, it looks a little bit like that. So why am I on this very far away, not very, but on these outskirts of the city? Well, because here next to this place that is also like very iconic, for sure you can recognize it, is the headquarters of a very famous coffee shop brand, Starbucks. Well, well, here are the headquarters of Starbucks. So nearby there is a more interesting thing, which is the Living Computer Museum, which is in a apparently dull-looking building, which is the one over there. But it's Art Deco, but very simple Art Deco. But the magic is inside. Why? Because there are machines like this one, which is a PDP-7, and I don't know if it has been shut down because of pandemics. But at that moment, it was still on and working, and it was the last one of these machines that was still operative at that time.
Which took 30 seconds to reach its target.
Oh my God, I stopped it again.
Their IQs may be somewhat higher than yours or mine. For them, it's all in a day's work to turn out a machine that not only has its own language and can practically think, but can even check on its own occasional errors and stop working until they're corrected. Compare the qualifications of this worker, an industrial robot adjustable to perform dozens of jobs with your own. And ask yourself how they might appeal to your boss. Automation produces fear. Workers dread the loss of jobs. Industry is afraid of alienating the public.
So, well, this video is played over there, and it says how different were things seen at that time. People regarded computers as something that could take their jobs away, as the woman is saying here in the video. And the term computer referred to human computers at that time, because rooms filled of mostly female women doing calculations by hand were used to calculate, for example, trajectories for missiles, bombs being sent to very, very far away. We are talking on a context of the Second World War. And then the computer rises, the mechanical computer rises as a way for substituting or change this. However, the term computer then was regarded as bad. And that's why at the beginning, the original computers were not called computers, but data processors. So the PDP, the DP of PDP is data processor. And very importantly, as I said before, maybe we don't take into account that our little phones in our pockets are descendants of these machines. And also, very interestingly, see the size of that computer, and that's only the storage part. They had to open, really to open the buildings so that they could come inside, because they were so big, so heavy. But well, that was the state of the art even in the 70s or the end of the 60s. So by the end of the 60s, there were 6,000 computers worldwide. And Frederick Whittington says that one is led to envision 26 from now how many computers the size of the cigarette pack and costing little more scattered around the country as thickly as empty beer cans. So he was right. He was like foreseeing something like this, no? The size of a cigarette pack, and it's a computer, portable computer, and it was difficult to imagine that that very, very big thing would get reduced to such a small thing. So that's programming in the 60s. And this is a slide that I like very much to show. First, because usually we say, well, maybe nowadays not that much, but maybe 10, 15 years ago, programming people we thought of men only, right? But no, there's a woman here, a programmer, and also she is very proudly showing the power of pencil. Why? Because programming was not sitting before a computer and running programs, but was writing programs by hand using a pencil and paper. That was how programs were written, and then they were converted into punch cards and executed, and you had to wait for 1 day or 2 to obtain your results. So things were very different at those moments. And also women programmers had several skills that, well, I cannot say men didn't have, but it was more difficult, for example, for a man to deal with so many small cables. You know, the brain of women and men are not exactly the same. So for several tasks, women are better than men and vice versa. But in this case, programming had to do a lot with cables and connecting cables from very complex configurations. So in this case, it was preferred to have women programmers at that time. Later things changed, and maybe nowadays we are seeing that again things try to have a balance, right? But maybe, I don't know, 20 years ago, programming thing looked like more a male thing. Well, not to go too deep into this thing, male, female, but here we have a puncher card. This machine allowed you to write the program and then convert into punched cards that maybe, I think you already know a little bit on this. However, this was what was fed into the computer, and here you can see how it looked. Or also you could be using paper tape like this one. This was even much more older. You can see when they were introduced, and you can see dates very old, going to the 19th century, 1846 or 1885. Because they were used, if you remember your classes from I don't know if in elementary school or maybe secondary school, you see the telares, I don't know how to say, these machines that help to automatically build very complex patterns on clothes that were semi-automated. And then Hollerith used these same pattern building devices to compute a census in the United States. So that's how punched cards came into to be famous. Hollerith is this one, the name Hollerith. So I don't know if I said this properly in English. I will repeat in Spanish. Que se hacían cálculos usando telares, pero más que cálculos era para hacer el patrón de la tela. Entonces eran como que uno por arriba, uno por abajo, un amarillo, un azul, y todo esto estaba codificado en tarjetas perforadas. Estas tarjetas perforadas fueron retomadas por Hollerith, quien las usó para hacer un censo en Estados Unidos y poder hacer el conteo muy rápido a principios del siglo XX. Estamos hablando de 1920 más o menos. Well, I hope I said almost the same, because I don't know how to say telar, this machine that works with doing patterns on clothes. So this is a problem. Next time I need to check this before. And well, of course, if you had the bunch of cards carrying here and there, sometimes they fell down and you had to sort them, each one of them spending hours and hours. So for this, no more problem. You have this machine from IBM, which sorts automatically your punched cards. So no more time spent on this. And this is from 1949. Well, you can read it. It can sort punch cards according to the position of holes into the card. And it was very fast, 650 cards per minute. This was also a working machine. This is also very interesting that all these machines were in a working state. Well, most of this. And how to interact with them? Well, we are so used to using a monitor and keyboard, but at those times, there was a thing called the teletype. And the teletype looks like a typewriter with a printer, a mix of a typewriter and printer, and the output was on the paper, as if it was a printer, and there was no screen, no monitor at that time. So you can see here, Hello World, and it worked with BASIC, and this is the PDP-7. And well, I think we are about to finish. The messages of error that these machines gave were very funny, like chess, like quit, exit. So like not so friendly, right? Just but well, that was how these machines worked. And even here again, quit, what? So yeah, very funny to work with these machines. Well, of course, the fault was mine because I had no idea on how to operate, and I wonder how they let me operate them with my ignorance. Well, I knew a little bit of BASIC, but only that, like print hello world, and it worked.
So not even for very short summers. So, right. So what I'm going to do is I'm just going to read the file directory off of this disk, just so you can see this thing in operation. It's the Model 33 teletype E-frame produced in 1962. It's the first appearance of the control key. And some models also the escape key. So there's a bit of trivia for you. All right. So you can see it's loud. Maybe not quite as loud as that, but now typing on this is a little bit challenging. There's about a half-inch travel and a whole lot of resistance. Let's take a bit of paper. We'll get a quick tutorial for us moderns, okay? This right here is what we refer to as a keyboard.
Well, and that's it. Time is over. I hope you want to know more a little bit on this. And maybe if you wonder why the hell the teacher is telling us about these very, very old machines, well, because I did the connection at the beginning of this class, because we had some of the algorithms designed in these machines from Thomson and Ritchie and other heroes we must remember, which invented Unix and of course C. So next time I'll tell you a little bit more on this story. I wanted you to have a